So we start. Today we are very happy to have a former UC Davis student, Lingfeng Li from Brown University. He will tell us about the new inflationary probe over axion dark matter. Take away.
Great. Thanks for the introduction. It's been a while, and I've witnessed some like a paradigm shift of the field. So I'm just actually moving a little bit more on compared to collider end, moving more to astro and cosmological side of the theory. So this is work supported by DOE and the NASA. And in this title page, I'm trying to create some remote connection between the field evolution and the collider physics. Okay, there's some ring right there, because the theme of this talk most likely will be cosmological-collider physics, and I will explain a little bit more in detail. So the talk would be based on two works, one recent one with my collaborator Xingang and my PI Gigi, and the work in last September with the former student Yunjia and Gigi. So as an outline, I'll just give a very brief introduction. I think you probably don't need that. Just like go through that very quickly. What's the axion, and also the cosmology perspective. And then, as the first part of the talk, I will just introduce a new mechanism, a very simple one, for post-inflationary axion, just how we're going to do to this scenario, and to just greatly enlarge the parameter space that's allowed, also leading to new observational hints. And then, as an independent part of this, I'll just try to introduce inflation itself as a cosmological collider. Basically, it's a very high energy, like a probe of unknown physics. Very, very heavy particles that you were never able to reach at the regular collider. And then trying to combine these mechanisms together and then give you how to collide axions in such cosmological collider, and then summarize. So I have to start with this strong CP problem. This is a little bit cliche. We need to start in this strong CP term in the Lagrangian, which is allowed in standard model, though it is not very well advertised these days. At least you cannot see them in the mug. That's also because we didn't really see this term right now. So instead of doing like all sorts of high energy observables, such a term, the strong CP term, show up in low energy observables, most likely in neutron EDM, the electric dipole moment of neutron. So you can imagine three quarks inside neutron, just like a water molecule. They may not perfectly align, and actually this theta, in a cartoon way, is related to the theta angle right here. And naively would expect, all right, let's put things together. So the diameter of a neutron, which is like of femtometer, and also the standard electric charge, some fraction there, I don't care. So naturally would expect something of 10 to the minus 13 ECM as the dipole. Of course, there are some loop factors right there, but eventually the current experimental bound turned out to be 10 to the minus 26, which means after some calculation, theta to be 10 to the minus 10. So this is a very small dimensionless number, and the theory originally tells you it could be order 1, pointing everywhere. So this is we have another nationalist problem right here. There's a dimensional number being small. So is there any mechanism behind this? So here comes the standard solution. One of the standard solutions, I think is still kind of popular in the community, is to call for an QCD axion, which is a brand of detergent, trying to just clean this mess away. So the idea is to use this pseudo number goes on of the PQ symmetry spontaneously broken. So after you just integrate out the heavy quarks compared to the axion, you were left with this dynamical interaction, A over FA, which is the scale of the symmetry breaking, or alternatively, the axion axion decay constant with the GG tilde. So once you avoid, like say, just plug in standard model chiral perturbation theory, and you work out the potential through some like simple algebra, you will find this potential, okay, just created by QCD, will actually minimize this in a way that this term vanishes dynamically once you're sitting in these minima. So it's not only because QCD axion or other sorts of axion-like particles is QCD axion is a good way to answer the strong CP problem, why the angle is so small. But also it is a natural candidate for dark matter. So more often than not, okay, as long as you have an axion field around, by definition, it's a good like dark matter candidate, because usually this like say scale FA of symmetry breaking is so high that it strongly suppresses any coupling with standard model, so it's naturally dark. And we know that dark matter uses up most of the matter budget of our universe, and we see their existence in many different channels, okay, multi-wavelength, multi-messenger, and multi-scales. So I think the existence of dark matter is just no doubt. The only problem remains is what's dark matter? So axion could be dark matter, and usually, as you have axion is a pseudo-scalar field, so it's like taken some non-trivial values. If we trace back to the inflationary era at the very early universe, where the vacuum energy just trying to blow up space-time and just create this very rapid expansion, we will see most of the axion dark matter stories, okay, if not all of them, involves its relation with inflation in a non-trivial way. So, in general, the axion cosmology can be categorized in two different scenarios or phases. The first one is called the pre-inflationary axion. So, in this sense, the scale of picosymmetry breaking is larger than HI inflationary Hubble scale over 2 pi, which is the effective effective temperature of inflation. So you can see that as the inflation as a quantity de Sitter space, and then you have a horizon out of it, and the horizon, once you have a horizon, you have Hawking radiation, and the Hawking radiation temperature of such de Sitter space can be recognized as a given Hawking temperature like this. So once this scale is greater than this, this is not a very precise limit, but conventionally people take this as a criteria for pre-inflationary axion. So during this phase, the axion, like say the picosymmetry is already broken during inflation, and you will have an axion, especially like you will have such phase, like say during inflation. So the picosymmetry is already broken, and we know that inflation is like a rapid expansion of space-time. So as long as the inflation just go on for long enough, a particular phase will just get expanded. So you take this small patch with like say uniform phase of axion, and it will exponentially grow, and after 60 eVols, it will just make the whole universe we observe today with the same phase. Of course, this is not a perfect mechanism. It cannot completely fix the value of theta, or like say the initial angle of A. There will be small perturbations. So you can think about this in two different ways. First of all, is the quantum fluctuation of A is going to create some spectrum of this isocurvature. Or you can equivalently imagine that A is not at rest, so the quantum fluctuation will move it, like say, and just make A with some, or just enforce A to have some random walk behavior. And this random walking of A will create inhomogeneities of A fields after inflation. And even very small differences will cause a great observational gap. So right now, these perturbations are strongly constrained by Planck. So this beta must be less than 0.038, and if you include the smallness of the primordial scalar power, curvature power spectrum, this tells you this value must be very small. So Fi must be much greater than H.
Sorry, AI and AS are what? Sorry.
AS is the AS is the primordial power spectrum, of like curvature we observe, right? The primordial fluctuation, okay, presumably coming from inflaton, which is 2.2 times 10 to the minus 9. That's the fluctuation level, and AI is just the power spectrum of isocurvature, and it's like not observed till date, so it's just some upper limit right there.
So, I mean, I'm just not familiar with this. So what sense is this a strong constraint? I mean, is the natural expectation it should be of order 1 or what?
It depends. Okay, it really depends on the ratio between the inflationary scale and Hubble. So right here, it just tells you this is
okay.
Yeah.
F sub I is the axion F or something?
Yeah, it's the axion F during inflation. It's basically of all the same order of FA. And this AS is 10 to the minus 9. So if you just put a 10 to the minus 9 right here, this tells you this whole combination is 10 to the less than 10 to the minus 10 or so.
Okay.
Yeah.
Okay, thanks.
All right, so as a cartoon, okay, just like further explaining what's curvature and isocurvature. The curvature, we know, okay, the universe must with some density fluctuation, right? That's why we are here. So you need to create some structure rather than just some homogeneous soup. And the primordial, like a quantum fluctuation of fields guarantees that. But still there are minor differences because we have different layers or different components of the universe. And how their oscillation or like say fluctuation is like related means something right here. So for the curvature, like perturbations, what you can see is, okay, different components, the fluctuation in a hand wavy way are like just correlate and just proportional to each other. While for isocurvature, though the total energy level, like say the net energy distribution is, okay, if you take this mode, it could be flat, but different components can do fluctuation in very different ways. And
the axion can induce this at the curvature perturbation because this axion coupling to this different stuff. No. Is that the reason couple differently, or
it's not really their coupling? It's just axion is converted to dark matter afterwards. And while all the remaining stuff we believe is coming from radiation.
Oh, you mean there are different sources? You mean?
Yeah.
Different
so
sources.
This is a typical feature when you have two different fields or
Okay.
fields
Yes, that's
at
true.
the end of inflation. So
You are saying axion will go to dark matter,
Yeah,
and
axion
inflaton will go to photon internal barrier.
Yep.
Okay.
Yeah, and what we mean isocurvature across this talk would be just dark matter versus photon, which is the thing that we observe nowadays, and it's like highly constrained.
Okay.
So in this sense, in this scenario where the axion is already present, and then it will go through like a misalignment mechanism and make dark matter later on. The thing is, a homogeneous, or almost homogeneous axion field will oscillate when the Hubble scale, well, because during radiation domination also, the universe lifetime becomes longer, so the Hubble scale is getting smaller and smaller. Once it's small enough, then the Hubble friction, like when you write down the EOM of axion motion, would just get suppressed, and it started to oscillate. Basically, it's due to, like, this happens during the time scale of axion frequency. So this oscillation, as long as you have an initial offset, which may fluctuate a little bit, but in general the same value, around the QCD minimum, you will create dark matter. So if you just trace the equation of motion and just trying to calculate the energy, you will find that the energy level actually falls with the scale factor A with the -3 power. So the co-moving energy density actually doesn't change. In that case, axion is behaving like whole dark matter. Or you can say that this coherent oscillation of this light field will actually create non-relativistic axion particles as dark matter. And notice that the axion dark matter density is depending on well, such initial angle to the second power. So if you have fluctuation right here, this will turn out to be dark matter or density fluctuation. That's how the isocurvature is introduced. Now we move on to the second scenario, which is the post-inflationary axion.
So there's sorry, because I'm not familiar with this. I know everybody works on this except me, but so there's a range of F axion where both of these things work. So where the
Yeah,
inflationary
I will go back to this.
You're going to go back to that, okay, yeah, so.
Yeah, I will show the map,
Right.
actually. So this is second scenario, which is a post-inflationary axion. So we just move to another phase of the theory where a temperature is much larger, okay, or larger than Fa, roughly speaking. Again, okay, what happens on the boundary is quite blurred nowadays. But one can also understand it in two ways. First of all, is that if the temperature is so high compared to the symmetry breaking scale, then you can imagine the thermal correction, right? So-called thermal correction is just strong enough to uplift the whole potential. So in that case, you don't have any symmetry breaking. Or you can think, okay, in an alternative way is the random walking, right? Because the axion random walks in the distance, okay, of all the h over 2 pi. So if this h over 2 pi is much larger than the Fa, so axion can actually just travel freely and rapidly around this bottom of potential. So effectively, at the large scale, you have no preferred phase observed. So in that case, at the larger scales, especially, there will be no isocurvature. The isocurvature only shows in the very, very small scales comparable to Fa, and at the larger scales, it decays through an exponential way, and therefore you no longer observe them. Of course, there will be still outcomes. For example, in that case, the axions will form topological defects till very late times. Okay, there could be domain walls, and even you set the domain wall number equals 1 to avoid their presence. The axion strings would be created, and they will be the dominant source of dark matter.
So okay, maybe one naive question. You're saying the symmetry is unbroken.
Yeah.
Why is there still axion?
Because the symmetries are broken during inflation, right? But nowadays, think about it, right?
No, I'm trying to say, during inflation, if the symmetry is not broken, you shouldn't have Gaussian boson, right?
Yeah.
That you agree?
You only have just
It's a normal degree of freedom.
yeah.
So
he's just saying that the symmetry is restored during inflation.
that I know.
Inflation.
You're saying the
consider
topological
temperature
defect
after inflation.
will develop after inflation,
After
after symmetry
inflation.
broken.
Yeah.
After symmetry broken.
Yeah.
Okay. Because if the pre-inflationary axion,
Yeah.
there's no topological defect. Any topological defect will dilute exponentially, right?
Yeah.
So that's the reason.
Yeah.
Okay, got it.
But go ahead.
The number of domain walls, that's not something you get to choose, that's determined by the dynamics, right?
Yep.
So
people play around this in multiple ways. You can introduce, just by hand, some a breaking, like a symmetry breaking between different minima. Or say in some theories, for example, you only have one generation of the heavy quarks that creates this minimum for you. If you have one flavor, then the domain wall number is 1. Just like a KSVZ type of theory that we're going to go through later.
so we know we have 3 generations of quarks?
It depends on how you couple the axion through quarks. Okay, so in that kind of theory, your axion doesn't couple to the standard model quarks directly, but some vector-like quarks heavy in the theory.
But isn't it just determined by the size of Fa?
I am not sure. Okay, in general, say the NDW, there was a DFSE type of axion that NDW equals 6 because you couple to all 6 standard model quarks. Or you can imagine in the theory that you introduce vector-like quarks, and there will be could be arbitrary, but in general you can introduce one of them, and then end domain wall to be 1.
Sorry, so why are we even talking about domain walls? I understand.
Not really.
strange-
Okay, I'm not really talking about domain walls.
I just want to understand because I certainly understand that there can be strings if you have a U1
Yep.
symmetry breaking. Why domain walls? Where are the domain walls even
Yeah,
coming from?
so let's go back to this slide. So this is a subtle point. So for example, right here you have the theory of
because
NDW equals 2, so you just go around it, there will be
It's the
2
number of
degenerate
local-
minimum,
Okay.
and then you have a wall
so
between.
Are you, so then are we discussing a scenario where you want to explain that dark matter is axions?
Yeah.
And so they're going to somehow come through these topological defects, or
Yep.
they're just
Yeah.
that's what we want.
Yeah, and the simplest case, and the people talk about most, is there are theories that you can go, say, just one minima, when you go through the circle, and then the strings are very interesting. Okay, there are numerous works on this, and
Yeah.
recently a lot of debate about, okay, just actual density, because everything goes through very complicated, like say, lattice simulation. And the most recent one, okay, they did a very good job, okay, in trying to model this, and they use different resolutions. Okay, there's a very technical business, all right, because these strings are very thin compared to the box. So you need to pay a lot of attention to how to control, like say, the numerics in your simulation. I'm not gonna just, I'm not gonna give an introduction to how to do this simulation, but the network with tension, okay, naturally with the scale FA squared would be formed, and these would just evaporate and cut each other, decays, okay, through the scaling law. So basically, in the box of Hubble, you will find like the length of the strings inside the box of scale Hubble, and then the network actually would like decay eventually once the axion gets mass at the low energy, or like the axion effectively becomes massive, and the dark matter density will actually mostly given by the string network, okay, like say the energy inside of these strings. And if you want full axionic dark matter, then the FA would be better of 10 to the 10 or 10 to the 11 GeV, depending on numerical details. Let's say.
Sorry, can I ask, should I think of this axion field that's being produced in this way as a classical field that somehow comes
Yeah.
from these strings unwinding? So
Yep.
it's not like they're axion particles flying around. It's some classical axion field.
When you do this calculation, people do consider, like say, it's just some classical like energy momentum tracing on the lattice.
But ultimately, this is again some sort of coherent state-like
Yeah.
state. with
At the very end.
classical-like. Okay.
Yeah.
Thanks.
So here's the guarantee, like say, the promised map of QC axion dark matter, like, okay, just different pieces of parameter space that you can like look for. So first of all, we know there will be like a line right here, which is like separate the two scenarios. So you can find like habitable regions in both ends. So right here you have a little delta, okay, the oasis, okay, I would say, where you are, okay, naturally free from like the isocurvature problem, and here the green like spot is just where the production rate is about the radial density you observe. Okay, below it's okay, but above you just overclose the universe. And right here are some projected future constraints. These are all projected constraints, I believe. And right here you have the pre-inflationary case. So it doesn't matter if what's your inflationary scale would be, because once the axion field is settled right there, and as long as you're okay with isocurvature, then the red density is actually determined by FA and the initial angle, like the theta right here. So the higher you have some fine-tuned initial condition, you may think, okay, there may be some mechanism to make sure that the theta is small. But anyways, in general, because of the isocurvature, there's like some inhabitable badland right here. You are constrained the inflationary scale to be less than 10 to the 9 GeV for the, like, if you are living in the pre-inflationary phase. So depending on point of view, this may not be a good thing, especially if you want to put everything closer to the gut scale, or you just want it to be observed in the future, because this part of the map, okay, the inflationary scale is bounded above by tensor to scalar ratio measurement, or like say just primordial gravitational waves. So if you wanted to see, like say this directly as a proof of inflationary theory, then you may want like just observables or like say theories living right here. So for pre-inflationary phase, that's a problem. For post-inflationary phase, it's just like getting limited nowadays.
So for these horizontal bands, they are the what?
Like a direct measurement bound. Yeah.
So
and
they
these
are
are
already bounded or something.
I think they are proposed, and they are only proposed nowadays.
Okay, so
and also there will be many stripes. Okay, they never show up.
They
This
are
is
not
great.
ruled out yet.
Yeah, they're not ruled out. Yeah.
Proposed.
Yep.
That
I will
they
show
can
the.
be covered in
Yeah, I will show the plot that with real bounds, let's say, and you will see it's not really any bounds. Okay, maybe some very tiny stripes, but not even there.
Sorry, just one more question about that plot. On the pre-inflationary case, there's a little tiny gap there between ADMX and Clash. I'm reading it correctly, right?
I think it's just some experimental setup, okay,
Yeah,
just
yeah.
how big,
No, no, I
yeah, it's
understand.
not really,
Okay.
I don't think that's like fundamental stuff, right?
Yeah, okay.
Okay, so let's now like do the question, okay, related to this paper with it, is that how can we expand the parameter space for the post-inflationary axion case? Because it's like some intrinsic nice feature of it. You have axion strings, so you may observe, okay, so for example, gravitational wave signals when this transition happens, or like say it's free from isocurvature, let's say. So there are some merits, and okay, it may also tell you differences in axion spatial distributions later on. So what can we do? Because it's like right now it's limited. Okay, right here is our own take. Right here just okay, not anything right there. You have the boundary. Below you have okay, just insufficient dark matter. Right here you have the right amount of dark matter, and that's it. It's not a okay, depending on point of view, it's not a huge parameter space. So what we are going to do is to rely on the fact, introduce the interaction between axion and inflaton, and then rely on the fact that the rolling speed of the inflaton field can be much, much greater than the Hubble scale itself. It's a little bit sarcastic. It's called like slow roll inflation, but this slow roll is just compared to the range of the field itself, but not compared to the Hubble scale. So we will see later on, okay, just numerically calculate how big this is, but in general, this is the fact. And once you have this rolling field, and once you have the interaction, you can use this interaction to uplift the potential. So originally, you would thought, okay, your theory lived in this space, but after this is lifted up, you have effectively a heavy field, and everything is trapped at its origin. So effectively, this is a okay post-inflationary axion. Even you have a large FA, or like say from the top-down view, like say just shrink this to 0.
Sorry, I just zoned out for a second. I'm sorry, but you don't really mean inflation, but there's some other scalar field that's oscillating that's doing this.
I literally mean inflation.
Okay.
Yeah. So I will let you know. Like say
This is what's happening. Right. This is what's just happening during inflation.
Yeah.
Okay.
Yeah.
Sorry.
So this is the heavy lifting mechanism, and if you find the like say original use is for like say just reverse the sign and introduce electroweak symmetry breaking during inflation. So the Lagrangian is okay rather simple. This is the only term that we add. All right. The remaining stuff are just naturally there in the theory. So you have kinetic terms. Okay. Blah blah blah. You have the potential. So we stay in this case we stay agnostic about inflaton potential. So you can plug in any theory you want. Here is just some hand-wavy potential for like the axion. So here's the chi is the PQ field, and the A is its phase, and the radial mode is just okay is absolute value. So it takes okay after inflation it takes a minimum of FA, and this is the term okay. And then by introducing this term, we just make sure. First of all, it doesn't break the PQ symmetry, so axion is still protected during inflation. And then the partial phi here, you also protect the shift symmetry of inflation, so it doesn't cause extra trouble. In principle, we can also plug in something that explicitly break it, but we choose not to, which is a safer approach. So the phi dot, okay, I have mentioned this in the last slide. The phi dot is actually related to the size of primordial power spectrum. So if you have single field inflation, then you can just actually calculate, because it's also just have this random walk behavior. So AS is actually suppressed by the phi dot squared. And since the measured primordial power spectrum of curvature is so small that it turns out the square root of this phi dot is about 60. So which means the phi dot is around like 3600 HI squared. And you put the square right here, so which means this number could be very large. Even that lambda also needs to be large, okay, to make the theory work. But in general, this is could be a large number to effectively uplift the theory. And the PQ symmetry would be safely unbroken if the effective mass is like heavy enough, okay, compared to, for example, 1.5 HI. So this is the traditional boundary when you have a scalar or pseudo-scalar field during inflation in the de Sitter space. The solution, if the solution is 1.5 HI, it behaves like a very massive field and it will not have any isocurvature at larger scale. So you just need to make sure that this effective PQ field mass is greater than 1.5 h. Okay, when you measure it at the origin.
Sorry, it's a little bit, sorry, can I, yeah, it's a little bit counterintuitive because you're assuming that HI itself is below the PQ scale, right?
Yes.
HI, right? Because otherwise you would, that would restore the symmetry and you wouldn't have to do all of this,
True,
right?
true.
So, but now this thing is triggered by HI, right? So in other words, phi dot, the inflaton dot is proportional to HI. It's going to 0 as HI goes to 0.
Yeah.
So this is an effect which is, it somehow ends up being bigger than the temperature HI itself, and
Yes.
yet it's driven by HI.
Yes.
It seems,
It's a little bit.
it seems a little suspicious. I mean,
Yeah, but this part is like, okay, just
is
confirm.
it just the number 60 that's somehow driving all of this, or?
Yeah, it's basically the number 60,
It's really
or like
a
say the
dimensionless
smallest
number.
of, yeah,
It's a dimensionless number that's driving all of this.
yeah,
And then lambda has to be, you're using a sort of a effective theory of inflation.
yeah.
point of
Lambda
view,
must
where
be
lambda
multiple
has to
times
be
greater
bigger
than
than
this one also.
HI.
Yeah.
You're making a very, whatever, conservative assumption that lambda has to be bigger than HI, but not
Lambda
bigger
is
than.
greater than, here, let me be a little bit more explicit.
Yeah.
Lambda must be greater than this, 60
Yeah.
HI, to be safe. Because you can just imagine like these
Yeah.
theories of like say phi dot will just infinitely go
But
into.
really, okay, but all these numbers are around HI
Yeah.
with some numbers.
Large
chosen
dimensionless
in-
numbers, which
large
is confirmed by
dimensionless numbers.
observation.
Okay,
Yeah.
thank you.
We are
Yeah.
using this fact.
Okay.
And this is like, okay, people trying to use all over different
Sure,
places.
it's fine. I just wanted to understand.
Yeah.
Thank you.
So, okay, because this is not the major part of this talk, I will just end it up right here. So there are a lot of like interesting details in the stories. So basically, this opens a new window free from isocurvature problems. Originally, your limit is right here, and once you introduce it, like say such a coupling, then you can go conservatively right here, and you can expand even more. So the thing is, you can live in this band, right? Because everything solely relies. You thought that your theory solely relies on, like say, the string network energy density, but this would work better if you have some like a mechanism to dilute the axion dark matter relative density. For example, you can have like early matter domination before BBN, but after the string axion string network decays. Or it could be even better if it's curvaton. Basically, in the curvaton scenario, okay, this would further go through the whole plane. But basically, you do not need to, like say, even you overproduce axion, okay, later on they get diluted. So you can go all the way up to, like say, 10 to the 14.5 GeV, and you have a large room open. And then most of these newly opened room, okay, right here, many of them would be compatible with the high inflationary scale. And therefore you have, okay, phenomenologically, you have a better chance to detect them directly through like a tensor to scalar ratio at the CMBS pole, say. So that's the end of the first part. Okay, this is a short paper.
Sorry, but sorry, do you want to go ahead?
No, just try to understand this early matter domination.
Yeah.
That's EMD you mean, right? That's the short.
Yeah. Yeah.
So that's naively you would say it's over closed universe, then
Yeah, you have the entropy injection afterwards, let's say.
Okay.
Yeah. I have backup slides for this.
Additional entropy to dilute.
Yeah. Yeah. They can be coming from like say the completely thermal story of inflaton, or you can like assuming another like a curvaton field during inflation. Like a curvaton field during inflation is that okay, the inflaton rolling speed could be even faster because it's no longer a single field inflation scenario. But it's a little bit lengthy. So let's move on to another question, which is related to the main dish today. The paper just put out like say 2 weeks ago is what if we apply the same mechanism, right, or similar mechanism to a pre-inflationary axion, so do some reverse engineering. So in that case, we would have, for example, like
You say 2 weeks ago, that's 22, 23, 23?
yeah, 2 weeks ago, right? Like
This year is only 23.
20.
Is there a typo in your
Yeah, I
archive
guess it's
numbers?
typo, right? Thanks for pointing this out, right?
Okay.
22, yeah, geez, okay, screwed up right here. Anyways, so the thing is, in this sense, you will have isocurvature, right? So naively you would expect, okay, inflaton is doing something non-trivial as isocurvature, and you would actually see, okay, a particular pattern. And indeed, what you would expect is the primordial non-Gaussianity, or you can also promote this idea to cosmological, so-called cosmological-collider, which like first developed by my collaborators Xingang and also Yi, and then later on, like Nima and Montesina revisited this idea in 2015, and they invented the name of cosmological-collider to make this thing really popular these days. The thing is that, okay, this phase of axion, right, as long as that's something non-trivial to do with inflaton, these fluctuations eventually of dark matter density eventually would be frozen at the late universe, and if you like just check the distribution nowadays, which they still are, so from these like a super toy showcases, you will see like say some fundamental differences. Though right here I inject crazy amounts of non-Gaussianity.
Sorry, what you're, I just want to make sure I'm following what you're doing. So you're taking that same coupling that you had before.
Or similar coupling.
A similar coupling, but now it's not big enough to restore the axion under inflation.
It's
but
a minor
but
adjustment.
it can still show up in these cosmological colliders.
Yep, exactly.
That's the idea.
Thanks.
Okay.
So the idea is, so naively, let's say if you have everything behaves like a free field. Okay, so you have like a bunch Davies vacuum of inflatons say at the very beginning, and then they all converted to curvature. And if they do look like free fields, then you do not expect like any non-trivial three-point correlations. So 2 points basically tell you everything. So every information is hidden in that, like a CMB, like a 2-point power spectrum.
Right.
But if there's like non-trivial interactions happen, then you would expect non-trivial 3-point correlations arise. Like ignoring a lot of like just numerical factors, but naturally scaled with the 2-point correlated square times some like a dimensionless number, and then this dimensionless number like also given by Planck limit, of course. Depending on the shape, okay, there are a lot of like kinetic details right here, but in general, right nowadays it's order 10. So we are not there yet. Okay, order 10 is not, okay, it's a little bit big for theoretical proposed models. It would be better if you get down to order 1 or order 0.1. Okay, but this is where we are nowadays. So, okay, now I have to,
it's going to get better. I mean,
it's going to be better, but there will be some limit. I will go back to this, but this talk is not really about observation. So I, as a collider, like a phrenologist, okay, let's say I'm still a collider guy, I need to start with a metaphor of regular collider. Okay, you can put in your favorite right here. But the general feature of a collider is that you prepare your initial states very carefully. So you just tune your beams and trying to aid them, cool them, or a lot of stuff happens to ensure the maximum production rate, of your target, Higgs production, etc. And in order to observe something, make a discovery of heavy resonances, that's nowadays how we observe, Higgs, top, etc. is observed. So you need once you create it, they create heavy resonances. Here is just a cartoon. And in general, which is a key difference, later on we will see, is these resonances are short-lived in general. And the short-lived means the mass is of multi-GeV scale in general, and the width in general is of all the same order. Maybe a factor of 2 orders of magnitude, but in general in the same ballpark. And we are not pushing our detector complex 1 femtometer away from the interaction point. It just doesn't work. So in general, we are just detecting the asymptotic information very far away. So compared to the mass, it's the detector is meter scales, infinitely big. And we have multi-species. Here I'm using photon as a dub. And finally, because we're living in flat space-time in this experiment, so you can use this basic technique in particle physics. You cannot live without this. just just invariant mass, you see a bump. That's how you make a discovery at the regular collider. So I'm going to squeeze this and just go to a cosmological collider, and there were a few fundamental differences. First of all, as I've mentioned, you are living in somehow like a thermal initial state. So you have no right to prepare the initial state. Instead, just like all these random bunch-Davies vacuum of some effective massless field, for example, inflaton. And by chance, they will create, just occasionally heavy fields, heavier than the inflationary scales, and this heavy field will propagate. And then because right now everything lives more or less in the ballpark of like inflationary Hubble. So the propagation actually, or like say the plane, everything lives in the same length or time scale. Eventually this field with the decay and these asymptotic modes, depending on what they are, will eventually just get frozen, after reheating, after the inflation ends, and just like you have different species projected to the detector plane, you may have like either isocurvature if this is an axion, or curvature if this is inflaton, or like say something else. For example, you have some mechanism to convert a vector boson into gravitational waves.
So should I be thinking of this as the heavy field is imprinting itself on the reheating surface, and then somehow later it decays into this, or should I think of it as it's somehow decaying
during inflation? Because its lifetime is
inflation.
These imprints are still asymptotic, so because we only see light fields, like say when they get converted after inflation.
So it distorts. I mean, these fields, if this heavy field wasn't there, these fields would have some
non-trivial correlation, right? Right here you can see they're correlated.
there, but this thing is distorting it. This heavy
Yeah.
field is distorting those.
Exactly. So yeah, I've mentioned there are some like critical differences. For example, the initial state is a little bit chaotic, so you need to rely on some quantum fluctuations. Though that everything happens at a very high scale, but you have no right to touch it. You may just imagine a lot of techniques with this this guy like say find these folks, but not the initial state. And then the detector surface is certainly closer to when it is produced or decayed. It also, because all these initial states, including these folks, will just randomly propagate. So actually they were full of these these fields already. So instead of observing the amplitude squared, actually you observe the amplitude, because you can always find, like say, some free propagating another half to interfere with. So actually you can see the phase right here. That's actually very important for cosmological-collider physics. And also the time invariance, just breaks down energy conservation, because you're full of vacuum energy right here. So you no longer do your invariant mass, right? You only see is like say angular correlators, or like say you boil down to momentum space, but no longer the energy part. So let's take a closer look and just zoom in what really happens there, and how on earth we claim we make a discovery using the cosmological collider. So first of all, it's just the thermal suppressed production, like say, because you rely on this gibbons Hawking temperature. So the heavier the field is, the amplitude, or like say the number that you produce is actually smaller. And they propagate and then at some point decay. And in general, because this field is heavy and initially you don't need a lot of momentum to create it, so the K decay you expect, for a heavy field is much larger than the K production. I will explain a little bit further. But that's what we use, the fact that we use. You can choose, right, what kind of K modes you observe and analyze nowadays. And because this gibbons Hawking temperature goes this way, so if you try to find out, for example, the amplitude, then this is an exponential suppression. And because this is the number of particles gets suppressed, and because the number of particles is more like amplitude squared, so amplitude itself is just the square root of this. Also, in general, you have, actually this is like, say, there are some specific correction right here, but if the mass is heavy, then this is a very good approximation, e to the pi m over h.
Sorry, so I understand the suppression if the mass is large compared to the.
Yeah.
Oh wait.
Yeah.
Sorry.
What's your point?
Yeah. No. There's. Yeah. You. This is the when there's all. Just go ahead. It's okay. Sorry.
All right. I may come back to
Yeah,
the
it's
points
okay.
that you
Go
wanted
ahead.
to arise. Yeah.
Yeah.
So how we make the discovery, as I've mentioned, okay, we rely on the phase differences instead of, okay, techniques like invariant mass. So what really happens is if we calculate the mode functions and trying to trace, this is the conformal time, it's basically some log of, okay, the actual time, t. The production, if you want efficient production, resonance production, then this happens when the k production and the tau, okay, just tracing the modes, is about order m. And the same happens for the decay. Okay, this is just a sketchy way to phrase it. And okay, this is much larger, so if you choose a different ratio of k decay over k production and work out the math, right? Because the propagator is actually oscillating with a certain frequency demanded by its mass. So if you plug in these two conditions, we will know, for example, if you choose the same ratio